Hi everyone, this is Mrs. GA, and today we're going to learn how to graph polynomial functions. So first, some important vocabulary that we'll need to know for today's lesson. First, what is a polynomial? So a polynomial is a function in this form. So p of x equals a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus dot dot dot. And then you can see it jumps down to a sub 2 times x squared plus a sub 1 times x, this should say to the power of 1 plus a sub 0. So what's happening here? What does this mean? So this means when it's in the standard form, the first term should have the highest degree of x. So if you see this is x to the power of n, the next term is x to the power of n minus 1, which means 1 less than the term before. And then that just keeps decreasing until we have our term with no variable, a constant, if it exists. So the degree of our exponent should be decreasing as we go down. And then this term in front, this is just the coefficient of each term. So when it says a sub n, that just means the coefficient when the exponent is n. Or when it says a sub n minus 1, it just means the coefficient of the term when the exponent is n minus 1, and that continues throughout. So kind of a different way of looking at the setup of a function, but something we should get used to, especially this concept of writing n minus 1, n minus 2. It just means that it's decreasing. Now, the next really important piece of vocabulary that we'll use a lot today is the degree of the polynomial. So by definition, the degree is the total of the exponents of the term with the highest power. For these, it's just going to be n. So you have to find the highest exponent. Sometimes your polynomial is written out of order. So make sure you're actually going through and finding what is your highest exponent. Okay, so lead coefficient, this is also going to be really important for what we're doing today, is the coefficient of the term with the highest power. So in this case, it would be a sub n. So again, sometimes it's written out of order, so make sure when you're looking for that lead coefficient, it's not always the one that's right out front. If it's written in standard form, it will be the one out front. And last, multiplicity. So multiplicity is the number of times a particular value is a 0 for a polynomial. So we know that a 0 is just simply another way of describing an x-intercept or a root. So sometimes a value can actually be a 0 multiple times for a single polynomial. So we call this maybe a double root or a triple root. And so that would have a multiplicity of 2 or 3. So we care about multiplicity because if the multiplicity is higher than 1, it has a special effect on what our graph looks like. So we'll be talking about that today. Okay, so here's all the steps you can follow to help you graph a polynomial function when the function is in factored form. So the first thing I'd recommend doing is listing out your zeros. And when you're doing that, make sure you make note of any multiplicity. So if there's a triple root, a quadruple root, or a double root, make sure you write it. Like I said, when you have a multiplicity that's higher than 1, it has a special effect on your graph. So if you have an even multiplicity, your graph is going to actually touch the x-axis and turn around. Okay, so that happens whenever we have an even multiplicity. And when we have an odd multiplicity, your graph is going to flatten out at that 0, but then continue through, just like it does with our cubic function. So we really need to make sure we know the multiplicity of our zeros to see if there's some sort of special feature we need to include in our graph. After you've listed your zeros, and you can even plot them on your x-axis, the next thing you should do is find the sign of your lead coefficient. So if your lead coefficient is positive or greater than 0, then that means the end behavior going to the right is going to be positive. So as x approaches positive infinity, f of x approaches positive infinity. And if your lead coefficient is negative or less than 0, then your end behavior going to the right is going to be negative. So the lead coefficient tells you the end behavior of your graph moving to the right. Okay? And then I like to make a little arrow on my graph or on my XY axis showing me that so I remember which way my graph will be headed. After you've done this, then you can find the degree of your function. And if your degree is even, then your end behavior will match. And if your degree is odd, then your end behavior will be opposite. So you can use the degree to help you figure out what's happening on the left side of your graph. I would also then find your y-intercept. Sometimes it's at the origin, sometimes it's somewhere else, but we can include that on our graph. And remember, we can always find the y-intercept by setting x equal to 0. And then we're going to determine if our graph is positive or negative over the intervals between our zeros. We'll talk about how to do that in the next example. And then it's just a matter of sketching your graph so everything fits together. There's lots of pieces to these types of functions, so then we have to just make sure it all fits together. Okay, let's give one a try together. So here we have the function x times x plus 2 times x minus 3. So notice this is in factored form. So the first thing we're going to do is we're going to list our zeros. So our zeros would be at x equals 0, negative 2, and 3. Remember, our zeros are always opposite of what we see in the factors. So if you want, we can even plot those. And here we're just doing a really rough sketch today. So we can even just label, or we could just give ourselves a couple tick marks. It doesn't need to be perfect. Here's negative 2, and here's 3. Now we can find our y-intercept. So remember, we can find our y-intercept by setting x equal to 0. So we could do that really quick. So it's 0 times 0 plus 2 times 0 minus 3. So our y-intercept is at the origin, which we see right here. Now we're going to look for the sign of our lead coefficient. So if, imagine we multiplied this out, our lead coefficient would just be this number right here. So here, if you don't see anything, it's a 1, and in this case it is positive. We really only care about the sign, so it's positive. So since the lead coefficient is positive, that tells us that moving to the right, our graph will go up. So I like to just draw a little arrow like this, kind of reminding me that our end behavior on the right will be positive. Now we need to look for the degree of our function. So here we have to essentially count how many zeros we have. That will tell us the degree. Really, if we multiplied this out completely, we would get a term that is x cubed, because we have x times x times x. So 3 is going to be the degree of our function. Really, again, you can count how many zeros you have, including multiplicities. So here we have 3 zeros, which means our degree is 3. So remember, since our degree is odd, that means our end behavior is going to be opposite. So if this side goes up, this side is going to go down. So I like to just draw a little arrow to remind me. So we can actually write in our end behavior as x approaches positive infinity, f of x approaches positive infinity, and as x approaches negative infinity, f of x approaches negative infinity. So again, we can find this because our lead coefficient is positive. We can find this because our degree is odd. Now let's talk about when our graph is positive or negative. So I'm going to actually just make like a little number line here. And I'm going to use my zeros to set different intervals for my graph. So we have negative 2, 0, and 3. So we're going to look at our function, and we're going to plug in a value within each of these 4 intervals, and we're just going to decide would that value give us a positive or a negative result. So let's start with some value to the left of negative 2. Let's just say f of negative 3. It could be anything to the left of negative 2. So if I plug in negative 3 into my first factor, which is right here, is the x, that factor is going to be negative. Now if I plug in negative 3 to this next factor of negative 3 plus 2, this factor is also going to be negative. And if I plug in negative 3 to this factor, the result will be negative. And if I have a negative times a negative times a negative, the result is a negative. Okay, so notice I'm not even figuring out what the value is. I'm just writing the sign of each factor. Okay, so in this region, everything to the left of negative 2, my graph is going to be negative. Now let's pick a value somewhere between negative 2 and 0. How about negative 1? So let's do a sign evaluation for -1. If I plug in -1 to my first factor, that's going to give us a negative. If I plug in -1 right here, that will actually give us a positive. And if I plug in -1 here into my third factor, that will give us a negative. And if I have a negative times a positive times a negative, the result is a positive. So my graph is going to be positive between -2 and 0. Now let's do the same here. So let's do, I don't know, +1. It can be anything. Our first factor will be positive. Our second factor will be positive. Our third factor would be negative, resulting in a negative. And then let's pick any number greater than 3. Let's just do 4. Our first factor will be positive, our second factor is positive, and our third factor is positive, resulting in a positive. So now we can see that our graph will be positive between -2 and 0, and from 3 to infinity. And it's going to be negative from -infinity to -2, and between 0 and -3. So now that we have all the information about our graph, all we need to do is piece everything together. So I'm going to start on the left. So I can see that I'm going to cross over here. My graph is going to turn around so it can cross again. And it will turn around so it can cross one more time. Now, this is a really, really rough sketch of our graph. So really, if we wanted a more accurate graph, we would need to make a t-chart to find some more values in between, because unless we do a t-chart, we don't really know exactly how high or how low our graph is going. Like, it could end up looking something like this, or it could be something like much flatter. It could look like this, right? All three of these graphs actually would work for all of the characteristics we found. So one thing that you'll sometimes see when you're graphing these types of functions, you'll sometimes see that we'll use actually dotted lines for everything in between to kind of show that it is just a rough estimate. So again, you'll see something like this. It'll be like a solid line here, maybe, and then it will be like a dotted line in between, and a dotted line, and then a solid line again. So it'll look something like this to show that, again, this is just an estimate of what's going on. It could go much higher, it could go lower, and again, it's just a rough sketch of our polynomial. So sometimes you'll see people graph it like this. I'm okay with just using a solid line as long as we understand that this is a rough sketch of our graph. Okay, let's try another one together. So here we have lots of zeros going on. So we can see that we have zeros at x equals, I'll just go low to high. So we have -5, -2, +1, and +3. So we can plot these on our graph if we'd like. We can do that now. -5, -2, +1, +3. Let's find our y-intercept. So let's plug in x for 0. So -0 plus 2 times 0 minus 3 times 0 plus 5 times 0 minus 1. So here we have a negative times a negative times a negative, which gives us a resulting negative, and it will be -30. So our y-intercept is at 0, -30. And again, since this is just a really, really, really rough sketch, let's just add in a line here, and let's just say, okay, this is -30. So we can plot this point. Again, super rough sketch. Now let's look at our lead coefficient. I see a negative out front. So our lead coefficient is negative. Again, we don't actually care what the value is, we just care about the sign. Since our lead coefficient is negative, that tells us as x approaches positive infinity, f of x approaches -infinity. So I'm going to kind of draw a little arrow to the right to remind me of that. Now we're going to look at the degree of our function, which really is just counting up how many zeros we have. We have 4 zeros. So if we multiplied this out, we would have a term that said x to the power 4. So our degree is 4. Now, since our degree is even, that means our end behavior is going to match. So as x approaches -infinity, f of x will also approach -infinity. So it's also going to go down. So again, any even degree, our end behavior matches. And now we can do a quick sign analysis for when our graph is positive and negative. So here is -5, -2, 1, and 3. So if we do f of -6 and we plug that into each factor, there is that negative out front. This would give us a negative times a negative times a negative times a negative. So we have 5 negatives, which results in a negative. If you plug in, let's say, -3, something in between the negative out front, this will be negative, negative. The third factor will be positive, and the last one will be negative, resulting in a positive. If you plug in something between -2 and 0, or -2 and 1, like 0, the negative is out front. Our first factor will be positive, then negative, then positive, then negative, and this results in a negative. Let's pick something between 1 and 3. How about 2? So the negative is out front. Our first factor would be positive. Our second factor is negative. Our third factor would be positive. And our second factor would be positive, resulting in a positive. And last region, so let's pick f of 4. We'd have the negative, and then this gives us a positive, a positive, a positive, and a positive, resulting in a negative because of that negative out front. So I know that it seems like, can't we just always alternate between the different intervals? The answer is no. Sometimes it doesn't always cross over at your 0. So it is useful to know how to do this sign analysis. Now all of our zeros have a multiplicity of 1. There's no double roots or triple roots, so when we approach our zeros, it crosses right through. So we need to make sure that we are only crossing at the zeros, and we're only crossing the y-axis at our y-intercept, and that we also match our end behavior. So this will go up through here, down through here. It will turn around here so I can cross there, and then it will end up facing back towards -infinity. So again, this is a really, really rough sketch. It could actually go much higher or much lower in between. But again, I'm fine with us just using a solid line as long as we all understand this is a very rough sketch of this polynomial. All right, now we're going to look at an example where we have a 0 with a multiplicity. So I see that we have 2 zeros. We have a 0 at -5, and we have a 0 at +1. But since this factor is being squared, this is what's called a double root. So the 0 at 1 actually has a multiplicity of 2. Okay, so I'll show you what that looks like on the graph when we get to that point. But here's, let's call this -5, let's call this 1. Those are my 2 zeros. Now let's find the y-intercept. So let's find f of 0. So negative times 0 minus 1 squared times 0 plus 5. So this negative value will be squared, so it becomes positive, but there's still this negative out front. So our y-intercept is at 0, -5. Again, super rough sketch. I'm just going to call this -5, and we can plot our point. We can see that our lead coefficient is negative. So that tells us as x approaches positive infinity, f of x approaches -infinity. So I'm going to draw a little arrow like this to remind me. And then our degree is 3 because we have a double root here. So 1, 2, 3. We have 3 zeros. So we're going to say the degree is 3. So when our degree is odd, remember our end behavior is opposite. So as x approaches -infinity, f of x will approach positive infinity. So I'm going to draw a little arrow to remind me. So again, our end behavior is opposite because our degree is odd. Now let's do a little positive negative analysis. So here's our interval. So we have only two zeros, -5 and 1. So let's pick a value to the left. Let's pick -6. We have a negative. If I plug in -6 into this factor and then square it, so negative, it's going to be a negative, but I'm squaring it so it becomes a positive. And then for my last factor, it will be negative, and this results in a positive. Let's plug in 0, so we have the negative out front. If I plug in 0 here and I square it, it's going to be a positive, or we can infer this factor will always be positive because we're squaring it. And then we have another positive resulting in a negative. And then let's plug in, I don't know, f of 2, so we have the negative out front. This one will always be positive, and this one will also be positive. So this results in another negative. So you can see here's a case where we didn't jump to the other side when we crossed over a 0. And this is because of this multiplicity. So whenever you have an even multiplicity, so here it's even because it's a multiplicity of 2. Remember, what happens to our graph is it's actually going to touch but turn back around. So it's not actually going to cross over at this point. So it kind of looks like a parabola at that point, like it touches and turns around. So now we're going to see if we can make everything fit together, keeping these signs and keeping our end behavior. And remember, you can only cross your axes at these 3 points. So it's going to go like this. At a certain point, it will turn around. And at 1, again, it touches and turns around because of that double root, because it is an even multiplicity. And you can see everything fits together, and our graph is positive and negative, exactly where it needs to be. Okay, we're going to try one more together. So here I actually have a triple root at 0. So I have a 0 at 0. And this has a multiplicity of 3. And then I also have a 0 at -4. So here's -4, there's 0. My y-intercept is going to be at the origin, so it's 0, 0. My lead coefficient is positive. So that tells us as x approaches positive infinity, f of x approaches positive infinity. So I do a little arrow going to the right. The degree of my function, so I have 1, 2, 3, 4. 1, 2, 3, 4. My degree is 4. Now, since my degree is even, my end behavior will match. So as x approaches negative infinity, f of x will also approach positive infinity. My end behavior matches. And now we need to talk about our sign analysis really quick. So here is -4, here is 0. So if we do f of, let's do -5, if you cube a negative, it stays negative, and then this would also be negative, resulting in a positive. Let's pick -1 for this one. Again, if you cube a negative, it's negative, but this one will be positive, resulting in negative. And then here, let's do f of 1. So if you cube a positive, it stays positive. This will be positive, resulting in a positive. Okay, so now we need to remember what happens when we have an odd multiplicity. So what's going to happen at this triple root? So when you have an odd multiplicity, your graph is going to actually kind of flatten out at that 0, but then it will cross through and continue going. So it's going to look like what happens with our cubic functions. So here, this is going to cross over at -4. It's going to come back and it will make kind of that S shape, and then it will continue through. So you have to do your best to show that you understand that it is flattening out but then continuing through. So we do still cross over our axis when we have an odd multiplicity, but we do have that extra little curved feature that you do need to show. All right, so at this point, I'm going to ask you to pause the video and give this one a try, and we'll check your answer in just a few seconds. All right, go ahead and check your work here. One thing to remember is at -3, since you have that multiplicity of 3, your graph is going to kind of flatten out but continue through. Make sure your end behavior matches and make sure you're only crossing your axes at these 3 points. All right, here's the last one for today. So again, please pause the video and give it a try, and we'll check your answer in just a few moments. All right, go ahead and check your work here. One thing to really check carefully is that you have that feature where your graph touches and turns around at +3 because it's a double root. We have a multiplicity of 2. Then check your end behavior and check that you're only crossing at your intercepts. All right, that is all for today's lesson. Thank you so much for watching.